5, section 5.1. Probability distributions. Definition. A random variable is a variable represented by X that has a single numerical value determined by chance. For each outcome of a procedure. Okay, so in this section, we're going to introduce the concept of a random variable and the concept of probability distribution. So a random variable is a variable whose value is determined by the outcome of the experiment. So you're gonna do a statistical experiment. Let's say you flip a coin, you roll a die, and the value of X determined by the outcome of the experiment. So its value is determined by chance. Okay. Now, in general, guys, when we work with random variables, we have two types. Types of random variables. Discrete and in this case, the values of X are whole numbers. Okay, so you conduct an experiment. The value of X is determined by the experiment, by the outcome of the experiment, but those values that we have for X are whole numbers. So X, you conduct an experiment, X is going to be a whole number, the output or the value of X. When the value of X is a whole number, then it is considered a discrete random variable. The other type is continuous. Continuous random variable, and in this case, the value of X is a real number. A decimal number, a measurement. Okay. In this chapter, in chapter 5, we're going to be working with discrete random variables. Next chapter, we're going to work with continuous. So we want to, in this chapter, we're going to work with experiments or procedures who's going to give us a numerical value, and that numerical value is a whole number, 0, 1, 2, 3, 4, and so on. So discrete random variables. Let me explain the concept with an example. Toss a coin twice. That's the experiment. Okay, we're going to toss a coin twice. X is the number of heads in 2 tosses. Right, so we're going to toss a coin twice. This is the entire experiment, very simple experiment. And after 2 tosses, we're going to record or determine the value of X. In this case, the number of heads in 2X is the number of heads in 2 tosses. Okay. So when you toss a coin twice, what are the possible values of X? Which is the number of heads. What are the possible number of heads? Well, when you toss a coin twice, the number of heads could be 0, no heads, or could be 1 or 2. How do you know that? How do we know that? If we look at what we call the sample space. In this experiment, when you toss a coin twice, the outcome of the 2 tosses could be heads, or heads, tails, or tail, head, or tail, tail. These are the 4 possible outcomes of this experiment. Either both tosses are heads, or the first one is head, second one is tail, the first one is tail, second one is head, and then the 4th possibility or the 4th outcome is that both are tails. So based on this, if we look at the definition of X, which is the number of heads, then the number of heads could be 0, could be 1, only in 2 tosses 1 head, or it could be 2 heads. So we're going to make a table here, 2 columns. This is called a probability distribution of X. We're going to put X in the first column and P of X in the second column. So again, X is the number of heads in 2 tosses. We toss a coin twice. And P of X is the probability of X. So, for example, one of the values of X is 0. What is the probability if we toss a coin twice, we get 0 heads, no heads? Well, how many of these outcomes have 0 heads? Only 1, which is the 2 tails. So the probability of 0 heads is what? 1 out of 4. What is the probability of exactly 1 head? Well, how many of these outcomes have exactly 1 head? Well, we have 2 outcomes. Either the first one is head, second one is tail, or the first one is tail, second one is head. 2 out of 4. So I'll put the probability of 1 is 2 out of 4. What is the probability of 2 heads in 2 tosses? Again, we have 1 possibility out of 4. So 1 out of 4. So these are the possible values of X and their probabilities. So this is what you see here is called a probability distribution. Probability distribution. You list all the possible values of the variable and you determine the probability of each value.
Wait,
Now,
so
if you want to check your work, I'm sorry, there's a question here.
yeah, is 0? Can you explain the chart really quick one more time? I'm just confused how 0 represents like 1/4 and so on.
Yes.
Thank you.
X is the number of heads. By definition, we want to toss a coin twice, and we want to count the number of heads in 2 tosses. Now, when you toss a coin twice, these are the possible outcomes. You have one of these possibilities. We have 4 possibilities, right? Now, only one of them, which is the tail, that's the one that where X is 0. Remember, 0 is the number of heads. So if you have 2 tails, no heads, that means X is 0, right?
Right.
So that value for X, which corresponds to only one outcome, out of what? How many do we have?
1/4. Okay.
Exactly. 1 out of 4.
How come there's not 8 outcomes if we flip it twice?
8 outcomes. Why? How do you get 8 outcomes? You're only tossing it twice.
Okay. All right. Thank you.
Yeah. Okay. The other 2 outcomes here, this is X is 1. Oops. Here X is 1. Here's X is 1. Here X is 2. So X is 0 is only 1 out of 4. X is 1, 2 out of 4. X is 2, also 1 out of 4. Now, to check your work, you're going to add all the probability values. The sum of these probability values, if you add them, must be equal to 1. If your values in the table are correct, then when you add the probability values, 1 over 4, 2 over 4, 1 over 4, you get 4 over 4, which is 1. This is how you check it. Also, you need to make sure that these probability values are always positive. You cannot have a probability value that is negative. Or you cannot have a probability value that's greater than 1. Okay? So 2 things you need to check. Probability distribution requirements. Number 1, the sum of all the probability values in the second column in this table must be equal to 1. 2, each value, probability value must be greater than or equal to 0 and less than or equal to 1. It cannot be positive, it cannot be negative, it cannot be more than 1. These are the probability values, probability requirements. If those are, satisfied in the table, then we call that table a probability distribution. A probability distribution. Okay. All right, let's take another case and construct a probability distribution. Example. Consider the following sample space. One, 2, 2, 2, 3, 3, 4, 4, 5. Okay. So we have this set of whole numbers. This is the entire set. This is the whole thing, not a sample. This is the population sample space. And the experiment is very simple, straightforward. We're going to select one number at a random. X is one number selected from the set at random. Okay. One selection, random selection from this set. Construct a probability distribution. That's our goal. Okay, so what are we going to do? Again, probability distribution is a table that consists of two columns. The first column lists all the possible values of X. Look at the set. What if we select a number? What are the possible values that we're going to get? X could be either 1 or 2 or 3 or 4 or 5. And then we're going to find the probability of each value. What is the probability of selecting one number and getting a 1? Well, how many ones do we have in this set? We have 2. Out of how many? 2, 4, 6, 8, 10. So 2 out of 10. That's the probability of selecting a 1 or getting a 1. And that is 0.2. What is the probability of selecting a 2? 3 out of 10. Probability of selecting a 3, 2 out of 10. Four, 2 out of 10. 5, 1 out of 10. That's the probability of each value of X. Check. What about the sum? Is it 10 out of 10? Yes. 5, 4, 7, 9, 10. 1. Check. Are these all values, probability values, positive and less than 1? Yes. So this is a valid probability distribution of X. X is in a discrete variable, random variable, and these are the chances of, or the probability of its values, right? The probability of getting X, selecting a number, getting a 1 is 2 out of 10, for example. Okay, so this is a probability distribution for this experiment. Okay. Next example. Example. Determine whether the following table is a probability distribution or not. Explain. This example, I'm going to give you a table and then you decide whether it is a probability distribution or not. X, P of X. 0, 1, 2, 3, 4. 0.15, 0.2, 0.37, 0.4, 0.05. Let's see whether the requirements are met or satisfied in this table. First, I need to check, is each value, probability value, greater than 0 and less than or equal to 1? Are these all positive or not positive? Greater than 0, less than or equal to 1? Yes. First condition is checked. Second condition, is the sum of all the probability values equal to 1? Let's find out. Let's add the values in the second column. 0.15 plus 0.2 plus 0.37, 0.4, 0.05. And the result is 1.17. We have a problem here. Since the sum of the probability values does not add up to 1, the sum is more than 1, that means this cannot be a probability distribution. You cannot have the sum of all the outcomes to be more than 100%. Probability of all the outcomes is more than 100%. So we're going to go here and say the sum of the probability values is not equal to 1. And therefore, this distribution is not a valid probability distribution. Period. This is not a probability distribution. Let's check another one. Here's another table. X, P of X. 0, 1, 2, 3. Negative 0.2, 0.4, 0.3, and 0.5. Okay. Is this a valid probability distribution? Yes, Sandra, the answer is correct. The answer is no. Reason? Reason is because the probability of 0 is negative. And the probability of outcome cannot be negative. The probability value is always between 0 and 1. Probability of an event so this is not a probability distribution since the probability of 0 is a negative number and probability value cannot be negative. Even though the sum is fine, if you add up the sum of these values is 1, right? But the second condition is okay, but the first one is not. The probability of an outcome cannot be negative. So this distribution is not a valid probability distribution. Okay, so be aware, guys, of this. You need to check the two conditions. Each probability value must be positive, less than 1. It could be 0, 0 is fine. And then the sum must be equal to 1. Okay. Now, the next point. Once we establish that we have a probability distribution, oh, by the way, before I do this, before I go into the next objective, yeah, no, I will go over the next objective first. Once we establish that we have a valid probability distribution, then we are required to do the following calculations. Okay. So, if the distribution of X is a probability distribution, right? So not every distribution is probability. If it satisfies these requirements, then you need to calculate two things. You need to calculate the mean value of X. And here I'm using the mean mu because now we're talking about the complete set of values of X. It's not a sample. We're not sampling here. We're just discussing X, the random variable X, with all the possible values of X, right? So the mean of X, you need to calculate that, and this is equal to the sum of X times P of X. And then you also need to calculate the standard deviation of X, which is the sum of X minus the mean of X squared times P of X. These are the formulas for finding what we call the parameters, the mean, the parameters of X, the mean, its mean value, and its standard deviation. Okay. So I'll give you an example. Example. Consider the following probability distribution. X, P of X. 0, 1, 2, 3, 4. 0.1, 0.2, 0.3, 0.15, 0.25. Find the mean value of X and its standard deviation. Okay, first I'm going to make sure that this is a valid probability distribution. I'm going to add all the values, probability values, and I'm going to make sure that it is equal to 1.3675. Yes, the sum is 1, and the probability value, or each of one of these values is between 0 and 1. So yes, it is a good, a valid probability distribution. Now, to find the mean, which is the sum of the products, you multiply each value, X value, by its probability. So take the first value of X, which is 0, and times it by 0.1, its probability value, plus 1 times 0.2, 2 times 0.3, 3 times 0.15, and 4 times 0.25. You take each value and you multiply it by its probability. What do we get? 0 plus 0.2 plus 0.6 plus 0.45 plus 1, and that will give us 0.8 plus 0.45 plus 1, 2.25. So let me explain what this means. It means that if you conduct this experiment many times, repeatedly, you continue to draw a value for X, then most of the time you're going to get a value between 2 and 3. the value of x most of the time is going to be within this, around this number here, 2.25. So it could be 2, most likely it's going to be 2, and few cases with 3. Sometimes you get 3. The 0, it might appear, you might get a 0, but very small chance. The 1 is also a small chance, but most of your values that you're going to get are between or 2 or 3. So that's the average. This is called the expected value. Mu sub x is the expected value of x. Now, what about the standard deviation? What do? I take each x value. First value is 0. I subtract the mean, and then I square the difference, and then I multiply by the probability value, 0.1. Right? So again, one more time. Take each x value, subtract the mean, take the square of the difference, and multiply by the probability of that x value. I'm going to write the formula again. Sigma x is equal to the sum of x minus the mean squared times the probability of x. Okay. So let's continue. Plus the next value of x is 1, subtract the mean, 2.25 squared, and then times this by the probability of 1, which is 0.2. And then the next value, 2 minus 2.25 squared times the probability of 2, which is 0.3. 3 minus 2.25 squared times 0.15, and then plus 4 minus 2.25 squared times 0.25. Questions? Continue. 2.25 squared times 0.3. 1.51875. Next value, 3 minus 2.25 squared times 0.15. 0.084375. Did I skip something? I'm sorry, guys. I think I skipped the second one. Let me go back. I'm working on this one here. Second one. Times 0.2. You guys agree with this number? 0.3 3125. And then the next one. Squared. 2 minus 2.25 squared. And then times this by 0.3. Point 01875. And then the next value I have, which is this. And then the last value, which is this one. Times 0.25. $765,625. And then I'm going to add these values, 1.5, 1875. Plus 0.765625. 2.7. Questions? Did anyone else get 2.7? Did anyone do a calculations here?
Professor, when you put these equations into the calculator, do you have to put parentheses around it, or does it make a difference? Like for the 0 minus 2.25 squared times the 0.1, do we put it in the calculator?
Yeah, put it in parentheses, right? And then you well, actually you subtract, right? 0 minus 2.5, you get the result, and then you square the result. Just raise it to the second power, and then times 0.1. Let me try it again. 2.25. So 0 minus 2.25 squared. You get a positive number, right?
Yes, I got 5.0625.
And then times 0.1. Oh, I made I'm sorry, guys, correction. I think your value is correct, Brandon.
Okay, yeah, because that's the part was throwing me off.
Yeah. I need me correct this. Apologize, guys. I made a mistake here. 0.50625. Is that what you have?
Yes.
Okay. So my first number, second one is good. This is good. Second. Yeah, I just made an error with my first number, so let me recalculate my total. And my total is going to be 1.6 0.875. And you're gonna put this under what? The square root. Actually, this is the variance, so this should be, can you please add the square root, guys? The square root for the standard deviation. So we're gonna put here square root. Square root. So this is the square is equal to that. So this is square root. So take the square root of the result, 1.6875. And that will give me 1.299. If I round to one decimal, I get 1.3. Okay. So again, guys, one more time, you need to make sure if you guys fix this, sigma x is the square root of this quantity. Okay. So you get this quantity. Once you get the sum, you put it under the square root and you get your standard deviation. All right, I want to show you guys how we're gonna verify this calculations. I know there's a lot of calculations here. It's very easy to make a small mistake and it's squaring or something, you know. So I'm gonna show you how to verify your work, your hand calculations with the calculator. Okay, so let's go back to the table. I'm gonna show you how to enter a probability distribution into your calculator and find the mean of X and its standard deviation. This table here. So let me share my desktop screen. Give me a second. Let me open that app. Okay. So guys, I'm gonna click the stat key. I'm gonna clear the memory first, make sure nothing is in the calculator stored from earlier calculations. So again, number 4, clear L1. And then I'm gonna also clear L2 because I have 2 columns here. So stat 4 and then second L2. Again, says stat, press 1, And then we're going to enter our X values in the first list. What are my X values? I have what? 0, 1, 2, 3, and 4. These are my X values. And then I'm going to move to the next list, L2. I'm going to enter the probabilities of these values. So 0.1, first probability value, 0.2, 0.3, 0.15, and the probability of 4 is 0.25. Okay, so this is our probability table. The X values are L1, the probability values are L2. Now press the Tab key, go to the right, calculate, select 1, and then list is in L1, move down, and here the frequency list you put L2. So second, L2. And then go down, highlight calculate, and then enter. Okay, look guys, it gives us our values. See here, X bar on the top, 2.25, that's what we got earlier, that's the mean. And then look at sigma. See sigma here, sigma X, 1.299, we rounded it to 1.3. Guys, did you see this? Any questions on it? Guys, can you hear me? Okay, yeah. So these are my verified, my data value, the mean and the standard deviation. Okay. All right, so let's go ahead and go back to the tablet. Okay. Now, let me explain, guys, why we are doing this. Why are we calculating the mean and the standard deviation of this variable? Again, here's the number line. The mean is 2.25. Now, add 2 standard deviations to the mean. Mean plus 2 sigma, 2 standard deviation. We get 2.25 plus 2 times 1.3 equals, so the mean 2.25 plus 2.6. 4.85. And then the other end, the mean minus 2 standard deviations. 2.25 minus 2 times 1.3. Minus 2.6. Negative 0.35. Guys, this range that you see on the screen here, this is called the range of usual values of X, or not significant values. All the values that are here, all the values of X, this range here, if my X value, any of my X values fall within this range, within 2 standard deviation, then we say that the value of X here are not significant. So again, it's not up to any one of us to determine statistically if an X value, if the value of the random variable falls within 2 standard deviation, then that value is not significant. If the value of X is more than 2 standard deviations, if it is here, then the X value here is significantly high. High value or values. If our X value falls to the left here, then it is considered significantly low values. Okay, so now let's look at our X values, guys. What do we have here? X is what? What are the possible values of X? X could be 0, 1, 2, 3, or 4. Do all of these values fall within this range? Within this range of 2 standard deviation? Well, this range is from negative 0.35 to 4.85. 0 is here. 1 is here. Within 2 standard deviations. 2 is here also. 3 is here also. 4 is here. All of them fall within 2 standard deviations. So none of the X values are statistically significant. Not significant. Or you can say these are usual values. Very likely to get these values. None of them is considered unusual value, meaning significantly high or significantly low value. These are considered all usual values. So all values of X fall within 2 standard deviations from the mean. Therefore, all values of X are not significant. Okay. Any questions, guys, on this section? Okay. Let's go ahead and move on, guys, to my next topic, next section here. (5.2) binomial probability distribution. So in the previous section, we talked about general discrete probability distributions. And today, in this section, we're going to focus on one specific distribution, which is called the binomial. Binomial probability distribution. I'm going to give you guys the definition, and then we'll discuss it. Let me take a picture of the definition. Okay. There is a procedure, there is an experiment, statistical experiment or procedure that occurs frequently in daily applications or real applications, which is called the probability or the binomial experiment, the binomial experiment. And this binomial experiment will result in what we call a probability distribution. Okay, so let me talk about the binomial experiment. Number one, a binomial probability distribution results from a procedure that meets these four requirements. Okay, what are these requirements? Number one, the procedure is repeated specific number of times. A procedure has a fixed number of trials, and that occurs, guys, when we select a sample, right? When you select a sample, every time you select an individual from the population, that selection is can be considered as a trial. Okay, so a trial is a single observation. The second condition, the trials must be independent, meaning that the outcome of any individual trial does not affect the probability in the other trials. The outcome of the experiment does not affect the outcome of the next trial. When you repeat that procedure again, the outcomes are completely independent, no relation between the outcomes of the experiment. Now, here's a very important condition. Each trial must have all outcomes classified into exactly 2 categories. Every time you conduct the experiment, you're gonna get only exactly 2 outcomes or 2 categories. Those 2 categories are commonly referred to as success and failure. And then the fourth condition, the probability of a success or the probability of a failure remains the same in all trials. In all trials. Let me give you guys a simple binomial experiment. Toss a coin 7 times. Let's talk about this experiment. Just toss a coin 7 times. Is this considered a binomial experiment or procedure? Let's find out. Is there any repetitions here? Yes. Now, first condition is satisfied. We have 7 tosses, which means we have 7 trials or repetitions. So this procedure is repeated 7 times. Number 2, are the trials independent? Means the outcomes are independent? Yes, independent. Trials. Right? When you flip a coin, the outcome, heads or tail, right? And the outcome of this toss does not affect the outcome of the next one. Still 50-50 chance of getting head or tail. So independent trial. Number 3. Do we have only 2 outcomes each time we conduct the experiment? In each trial, do we have only 2 outcomes? Yes. Each trial has exactly 2 outcomes, head or tail. Number 4, is the probability of head or tail the same in all trials? Yes, the probability of head is always 0.5 in any of the trials. Same thing for the probability of tail is 0.5, 50%. And that remains the same on all the trials. So because these 4 conditions are satisfied, then I can say that tossing a coin is a binomial procedure. is a binomial procedure. But let's look at this example, guys. Roll a die 7 times. Is this experiment a binomial experiment? First condition, 7 rolls. Yes, that means 7 trials. No problem. We have 7 repetitions. We are rolling a die 7 times. And number 2, are the outcomes independent? When I roll a die and I get 5, in the next roll I can get also a new number. There's no dependency here. The outcomes are independent. So therefore, independent trials, no problem. 3, does each roll or each time we roll a die, do we have only 2 outcomes? The answer is what? No. Each trial has more than 2 outcomes. One, 2, 3, 4, 5, 6. So each trial has more than 2 outcomes. So it is not binomial. So we stop here. Since each trial has more than 2 outcomes. Oops. Because this is not satisfied, therefore the result is rolling a die 7 times and observing the output or the outcome is not a binomial experiment.
Wait, it is or it is not a binomial experiment?
Is not, thank you. A binomial experiment is not a binomial experiment. Okay. Now, if the experiment is a binomial experiment, then we can use what we call the binomial formula to find the probability of X. Let me go back here, guys. So I want you to focus with me on these variables. Again, I'm going to use S for success, F for failure. P of S, the probability of a success, we're going to use the variable P for it. And the probability of failure is Q, which is 1 minus P. Remember, each trial has only 2 outcomes. Success, one of them is called success, the other one is failure. Usually we call the outcome success if we are interested in observing that or seeing that outcome. Failure is for the other outcomes that we are not interested in. N is used for the number of trials, X for a specific number of successes. in n trials. So x can be any whole number between 0 and n. And said is the problem. And then P of x, that's the probability. Look at the description here. Probability of getting exactly x successes in n trials. Now, here's the formula that we're going to be using. The probability of x is n factorial over x factorial times n minus x factorial times p raised to the x times q raised to the n minus x. This is called the binomial probability formula. Let me, guys, give you an example on using this formula. Find the probability of getting exactly 4 heads in 7 tosses. Toss a coin 7 times. What is the probability of exactly 4 heads? Look, I'm tossing a coin 7 times. So that's my n. N is 7. I'm interested in getting exactly 4 successes, 4 heads. So x is 4. Exactly 4 out of 7. 4 heads in 7 tosses. And then what else? P, what is the probability if I toss a coin once? What is the probability of a tail or a head? 0.5. Probability of head is 0.5. And Q, which is the probability of a tail, which is 1 minus P, is also 0.5. These are my values. 7 trials, 7 tosses, 4 successes, 4 heads. P is the probability of success of probability of a head is 0.5. Q is the probability of a tail is 0.5. So to find the probability of exactly 4 using the formula, what? 7 factorial over 4 factorial times 7 minus 4 factorial times 0.5 to the 4th times Q, which is also 0.5 to the 3rd power. 7 minus 4, 3. So 7 factorial, that's 7 times 6 times 5 times 4 factorial over 4 factorial times 3 factorial. And then 0.5 to the fourth, 0.5 to the third. Cancel these. Remember, the 3 factorial is 6. The 6 will cancel with the 6. So that's 35. And then 0.5 to the fourth times 0.5 to the third. And that is equal 35 times 0.5 to the 7th power. 0.2734. Or in percent form, 27.3% probability of getting exactly 4 successes, 4 heads, and 7 tosses. Okay. Questions or guys on my hand calculations? Okay. Verify. Let's verify with the TI calculator. Can you please mute your mic? So I'm going to show you how we're going to verify with the TI calculator. Let me switch screens. All right, so share screen. Okay. All right, guys, focus with me on this. First thing I'm going to do, I'm going to select or click on the second key, second vars. So one more time, second vars. And that will give me a list of probability functions that we're going to use. Okay. I'm going to scroll down all the way to binomial PDF, this one. Binomial PDF. I'm going to select this function. And then I'm going to enter the number of trials. I'm going to toss the coin 7 times. So N is 7 trials. And then I'm going to enter P, the probability of success, not Q. What is the probability of a head or a tail? A head is 0.5, so 0.5. What about the number of successes? How many successes I'm looking for? I want 4 heads and 7 tosses, so I'm going to put 4. And then enter, and then enter, And this is now my function, binomial PDF. N is 7, probability of success is 0.5, and we're talking about 4 successes. And then I enter, and I get 0.2734375. If I round 0.2734, this is exactly what I got using the binomial formula. Okay, did you follow me, guys, with this? Okay. Let me do another one. Another calculation. Okay, so I showed you how we're gonna re-verify it with the calculator. We got 0.2734, and that's what the calculator gave us. Let's do another one. Okay. Given that there is a 0.85 probability that a randomly selected adult knows what Twitter is. Okay, I'm giving you an assumption information. I'm telling you, assume that the probability, if I randomly select an American, an adult, the probability that this person that I selected randomly knows what Twitter is 0.85, 85%. Okay. Ten are selected at random. Find the probability that at least 7 out of 10 know what Twitter is. Okay. So, is this a binomial experiment? The answer is yes. We are randomly selecting individuals from the population. How many are we selecting? 10. So n is 10. 10 trials. We're asking, that selected person is either gonna know or does not know, knows or does not know what Twitter is. Now, what is the probability of knowing? What is the probability of success that the person knows is 0.85. What is the probability of failure? In this case, the person selected does not know. What do? I subtract 0.85 from 1, 0.15. So P, probability of success is 85, failure 15.15. 15%, which is 0.15. I'm interested in finding the probability of what? I'm interested in finding the probability that X is at least 7, which means X is greater than or equal to 7. At least 7 means 7 or more in a sample of 10 know what Twitter is. So X is greater than or equal to 7, and that means the probability that X is 7 plus the probability that X is 8 plus the probability that X is 9 plus the probability that X is 10, because we have a sample of 10. So either 7 or 8 or 9 or 10 will know what Twitter is. And then we're going to find the probability of 7. And in this case, we're going to use our calculator. So binomial PDF 10, probability of success is 0.85, and then X, which is 7. So you're going to put N P X. And then you're going to do this for all the values, P of 8, $10.858, and probability of 9, again 10.85. See, the first two numbers are not changing, only the X value is changing. And then the probability of 10, binomial PDF 10.85, and then 10. And then we're going to get these values from the calculator. All right, guys, so let's do the first one. Again, go ahead and press the second bars key, the blue key, and then the bars key that will give you the distribution list. And then go down binomial PDF, 10 trials, 0.85, and 7. .1298. And then the next value. Are you getting the same numbers I'm getting, guys? Binomial PDF 10.85, and then next value is 8. And that will give me 0.2759. I'm rounding to 4 decimal places. And then again binomial PDF 10.85. Now nine successes. And that will give me 0.3474. And then the last value, the probability of 10 successes, all right, 10, this is 10, paste, 0.1969. And then I'm going to add these values to get the probability of at least 7 to 10. So I'm going to add these values. 1298, 2759, 3474, and then the last one, 1969. 0.95. 95% chance that at least 7 out of 10 randomly selected adults will know what Twitter is. 95%. Okay, questions, guys, on this? So always you need to know what number of trials is, when n is. You need to know the probability of success. Usually the example or the problem gives you the probability of success. This is all what you need. You don't need to find the probability of failure, just P. And you need to know exactly what number of successes you're calculating or finding the probability of. Okay. Guys, when you have a variable, just the last thing before we conclude, if you have if x is a binomial variable, a random variable, then the mean value of x is n times p, and the standard deviation of x, these are formulas only for binomial variables, it is the square root of npq. Which means for this case, guys, for the Twitter example, what is the expected value or the mean value of x? Well, let's see, what is the number of trials? N is 10. What is the probability of success? 0.85, so that will give me 8.5. So if we conduct this experiment, and if we select a sample of 10 individuals, we should expect that between 8 and 9, right, 8 to 9 individuals in the sample will know what Twitter is. 8 to 9. Average 8.5. What about the standard deviation of this variable? Square root of 10 times 0.85 times 0.15 q, and that gives me the square root 10 times 0.85 times 0.15, and that will give me 1.1 approximately standard deviation. These are the parameters. If you're asked to find the mean and the standard deviation for these variable, these are the formulas for the mean and standard deviation.